So, okay, so I think I can share my laptop screen. Okay, so let's get started. So in the previous class, we learned about some basic architecture of the pipeline processor. Actually, I said it is called the statically scheduled pipeline. So actually, every digital systems have pipelines, which means that the functions are split by some stages, pipeline stages, and then when the clock is propagated, the functions and then some executions are also propagated via pipelines. So actually, I believe you are familiar with the architecture of the 5-stage pipeline. So actually, the 5-stage pipeline is composed of 5 steps: instruction fetch, instruction decoding, execution, memory, and write back. Okay, so actually, so why do I start with the basic 5-stage pipelines? So actually, we learned that in the 5-stage pipeline architecture, these stages are required stages for executing instruction. So we need to fetch instructions from instruction cache, and then decode the instructions, and then the decoded instructions are executed by execution units. Then the result is returned back to the register file. So actually, in this course, we will learn about the architecture of a GPU. Then, as I said, GPU has many wimpy cores, and then these wimpy cores do not have any prediction technology or prediction architectures. It's very simple. So which means that GPU has many simple cores, and then using these many simple cores, so GPUs can execute parallel the many thread concurrently. So GPUs can support parallel processing efficiently. So actually, the architecture of this individual core of a GPU actually it's different, but the pipelines of GPU core is actually similar to this 5-stage pipeline. So I said it's different. It's different, obviously, but also the pipelines of the GPU is not dynamically controlled. So the GPUs can also support branch instructions. So also GPUs can support divergent execution path, but GPU pipelines are also statically controlled. You need to also remember that. And then what is important in the 5-stage statically scheduled pipeline architecture? So we need to handle hazards. Hazards are very critical for performance of process architecture, because if hazard occurs, then clock cycles are wasted. So we need to reduce the influences from hazard. So in order to reduce wasted clock cycles by hazard, the 5-stage pipelines architecture also support data forwarding. So actually, there are 3 kinds of hazard: structure hazard, data hazard, and control hazard. But usually, the data hazard are caused by instruction, the data dependencies observed in instruction. And then, in order to reduce the wasted clock cycles by data hazard, 5-stage pipelines support data forwarding. So which means that the required data, if the required data is already generated in the processor, then generated by actually execution unit, then this data can be delivered to following instructions. Okay, but GPU architecture does not support data coding. Okay, so it may be amazing, but it's true. So GPU also solves the influences from data hazard by using multi-threading. Okay, we also in this class I will also cover the multi-threading, the CPU architecture. So actually, we are reviewing the CPU architecture. Also, actually, in the statically scheduled pipeline architecture, the latency of a floating point unit and then integer units are different. So it is because the floating point units are is more complex than integer execution unit. So that's why the latency of the floating point unit is lower than the higher than the latency of integer execution unit. So actually the stick pipeline architecture, the processor also supports this issue. So and the latency of these execution units are different, the divergent. Then we need to also consider the hazard of write. So like the wow hazard, right after write hazard, or war hazard, right after read hazard. Okay. So actually we need to consider also the precise exceptions in the out of order completion pipelines. Okay. So actually the these out of order completion issues are handled by scoreboard in the processor. Okay. Okay. And then in this time I will also cover the CPU architecture. Actually, it's a traditional architecture. But I briefly cover this CPU architecture. So as you can expect, I covered the statically scheduled pipeline architecture. So in this time, I will cover there's dynamically scheduled pipeline. So actually, this is very critical. It's very critical for the performance of modern CPUs. So our order execution. So it is, and we frequently call the out of order processor the OOO. It's a 3O, but it's out of order. Actually, the middle O is the lowercase, so it looks like some surprise case. Okay, so out of order execution is critical for the performance of CPUs. So it is because the processor is applied, which means that think like this. So it's a load instruction and then add instruction is following the load instruction. So actually we know that if cache miss is incurred for this load instruction, then load instruction will take very large amount of cycles. Okay, so it will take very long time until the load instruction receives data from the low-level cache or memory. And what's the problem? If this add instruction, so if we focus on this add instruction, and then if the add instruction does not use any result from this former load instruction, then we can actually the processor can execute this add instruction because all operands are ready because there is no dependency between this load instruction and add instruction. So let us assume that all operands are ready. So actually the processor can execute this add instruction, but problem is that the add instruction is following load instruction. So in the statically scheduled pipeline architecture, it cannot use actually the processor the processor cannot execute this loading function, even though the processor can actually it can execute this adding function because the all operands are ready, but processor cannot execute because it's the in order execution. But so in the first class, I explained that processor can improve performance using instruction level parallelism. So what is the instruction level parallelism? If we can increase the number of instructions which can be executed simultaneously, then we can increase the performance. And what is the problem of the the process architecture? It's a statically scheduled process architecture. Even though the all operands are ready, so processor can execute this instruction, but this instruction cannot be scheduled for execution, which means that the number of instructions which are being executed in a processor is very small. Okay, so and then actually the solution is simple. So all operands are ready, so which means that processor can execute this instruction, and then actually this load instruction is stuck in the load store unit. It's a load store unit, which means there is a memory hierarchy, so memory pipelines. So actually this add instruction can be executed by integer execution unit, which means that if ready, then we can execute. This is the concept of dynamically scheduled pipelines. So it's actually idea of out of the processing. Okay. So I explained this. So I said that traditional CPUs can increase the performance by increasing the number of instructions, number of concurrent instructions, which is the instruction level parallelism. Then how can we increase the instruction level parallelism? It's the out of execution. Okay, out of order. Out of order execution. Okay. Then what are challenges? So actually, we need to consider the all type of data hazard. So actually, the data hazard are caused by data dependencies between read and write. Then we also consider that data hazard in actually when instructions are executed in a processor and data, the result of instructions are stored in two places. So register file first, and then the second is the main memory. Okay. So main memory is stored by load and store only. Oops. Okay, and then many instructions for results to register file. Also, many instructions read occurrence from register file. So actually, we need to consider hazard, hazard caused by data dependencies between read and write. Okay, actually, write is very critical because write actually read. So let's think about the read. It's just to read data from memory, but if we read some data from memory, then the states of processor are not changing. Okay, the states are just same. So we do not consider about the read, but write is critical because write change the states in processors. That's why we need to focus on the write. So actually, we can think about four types of hazard, but we don't need to consider what the read after write, because read does not change the state. So we need to consider these three types of hazard: low hazard, war hazard, and wow hazard. So it's very important. Actually, low hazard is the true dependency, but war hazard and wow hazard are caused by out of order execution or out of order operation. So when the execution instruction, when an instruction is executed, then what is the result of instruction? The result of instruction is just write some data to register file or memory. Okay, these are final results of instruction. But when the instructions are executed out of order, then with the order of write and read can be changed. Okay, and that's the problem. So we need to consider the war hazard and wow hazard when we implement out of order execution processor. Okay, so war hazard means that, so actually we need to keep the order of read and write here actually. So this is the war hazard. Also, we need to keep the order of write and write. Okay. Okay. Like this is the example, and then this is the example. And this order is changed, then the add instruction. This add instruction comes. This add instruction, if this add instruction is executed earlier than this add instruction, is a formal add instruction, then what's the problem? This add instruction will read wrong data from R3. So that's why we need to keep the order of read and write. If the target register is the same, and the wow hazard is also the same issue. If the disorder is changed, then R2, after these two instructions are executed, this R2 will have wrong data, incorrect data. So which means we need to also keep the order of write and write. So actually in this slide, I show the examples of war hazard and wow hazard in register file, but we need to also consider this war hazard and wow hazard in memory, right? So actually this is, so the register file is actually simple, it's a simple issue because we, so we have just tens of registers, right? So which means we just check the relation between 32 registers or 64 registers in a processor. But if think about the main memory, how can we check the some target space, the target position in the main memory? So we need to check the address, but the size of the main memory is extremely large. So it's very difficult to check the relation between read and write using addresses in main memory. But it's true, we need to check the war hazard and wow hazard in main memory. Actually, it is for difficult issues in a processor. Okay? But in this class, I will focus on the hazard in register file. Okay, this is the critical challenges in that's out of order execution. Okay, so challenges that we need to consider all possible data hazard in registers, also actually in memory also, and then branch. So why branch is critical for the performance? So when the branch is executed, then there can be two different execution paths by the result of the branch. If the branch is true, then these instructions in this path will be executed. And then the branches false instructions in this path will be executed. The problem is that if we do not know the result of branch instruction, then processor also does not know which instructions will be executed after branch instruction. Then what is the goal of the advanced architecture? So goal of advanced architecture is to increase instruction level parallelism, which means that increase the number of concurrent instructions. The problem is that branch. So as I said, we don't know which instructions will be executed after branch instruction. So if we execute these instructions, then these instructions will also update the stage in processor, like register 5 or main memory. Okay, but if the expected result is wrong, is incorrect, then how can we? So actually, we need to cancel these executions, and we need to also execute this old path after the branch instructions. So problem is that if a states are already changed, it's not easy. It's very difficult to roll back the changing states in a processor. So that's why. So the branch instructions are also critical for the performance of a processor. Actually, when we consider the instruction level parallelism. So usually, if we just implement the out-of-order execution, then we need to stop at branch instructions. What problem is that? Branch instructions are observed every 4 to 5 instructions. So which means usually a processor has only 4 and 5 instructions before branch instruction. We have only 4 and 5 instructions, and then which means the processor needs and maximum the processor has only 4 and 5 instructions which can be executed concurrently. How can we increase the instruction level parallelism? So we need to increase the number of instructions. So we apply speculative execution. So predictive, actually, we can call it as the predictive execution. Okay. So we apply speculative execution. And then another issue is the exception model. So a processor usually a processor needs to support precise exception. So exception is the abnormal result of instruction. So actually, a processor needs to report the which exception events are occurred in each instruction. Okay. So which also the exceptions need to be handled order of instructions. So for example, so this is the load instruction, this is the add instruction, and then the exception happens for both load instruction and add instruction. Exception. But processor needs to handle the exception in load instruction. But if the instructions are executed out of order, then exceptions in add instruction can be effective earlier than the exception in load instruction. Then the processor a processor may report the exception for add instruction, but if the exception for load instruction is detected, then processor also need to report this. But problem is that this exception should be handled first. Okay, so actually, processor need to support the precise exception. So these are challenges in out-of-order execution. So why? if the execution orders are changed, then you need to check handle these issues and these challenges. Okay, then how we can implement the out-of-order processor architecture? So actually, this is the architecture of statically scheduled pipeline architecture. So what a change. So actually, this architecture is very similar to this architecture, but the only change is that memory pipelines can be executed in parallel with the integer execution and then floating point executions. Also, but other things are the same. So if we see this pipeline architecture, this is the instruction fetch stage, this is the instruction decoding, and then this is the execution stage. But the memory stage are also here. So the address is generated. So each and then address of load or store instructions are calculated, and then the cache is accessible. Also, we can find the write-back path from each execution unit. So it's a write-back path from integer ALU, and then when the data cache is accessed, and we need the result of this load instruction. So load instruction can access the integer data or floating point data. So after this data cache, the data can be written back to both integer register file or floating point register file. Also, the output of floating point execution unit is written back to the floating point register file. So this is actually the typical statically scheduled pipeline architecture, right? So and then we say this is actually the memory, and then it's a write-back stage. Actually, we can start from this dynamically statically scheduled pipeline architecture to implement the out-of-order execution. Okay, so it's the same. The PC is here, the instruction cache is here, but as you can see, this is elongated. So actually, so this is the design policy of this design. So actually, in order to change the order, actually we want to change the order. We want to change the order of instructions, and sometimes these execution engines have different latencies. Okay, actually the different instructions have different latencies. Then how can we handle this situation? So which means that this is the sender, and then this is receiver. And then sender sends some data or instructions to receiver. But if this frequency, so the frequency of sending some data to receiver is fixed, and then if the throughput, so the frequency of processing data or instructions is fixed in the receiver, then we can send some data or instructions to receiver without any memory components. Because we don't need to control the order of instructions, and then the frequency is the same, and then if the speed of the sender and receiver is the same, then you can just can send data or instruction to receiver without any memory components. But if the frequency, if the instructions or data are processed with the area frequency, so which means that the latency is divergent. Also, we don't know when this request can be serviced by receiver. So in this case, we need memory component, right? It's the design policy, it's a basic design policy in digital design. There is a sender, there is the receiver, and then the processing frequency of the receiver is divergent. And then actually, you don't know when the receiver completes the request, the processing, the request from sender. So in this case, we need memory component called a queue, right? So for queue, okay, first in, first out. Also, we can change the order. So, but actually, in this case, we require a queue, okay? And then it's the same for the hourable execution pipe architecture. So instructions are fetched from instruction cache. So, actually, if the instruction is fetched, then this fetched instruction can be sent to the next stage. But actually, the bit rate of the instruction cache is very low. So we can assume that we can send instruction to the next stage very regularly. But it's not true, but usually. So we can say that, oh, this is the sender. Okay. And then this next stage is the receiver. So actually, this is the instruction decoding stage. When the receiver is the instruction decoding stage, receives instructions from instruction cache. Then this is the out of order execution. And we can the decoder, the instruction decoder can change orders of instructions. Okay. So which means that some instructions need to stay longer after the instruction fetch stage, and then or some instructions can be decoded earlier. Which means we need to add queue. So this is the queue. So queue. I need to avoid touching. So this queue is the instruction fetch queue. So because we have instruction fetch queue, and we can also okay, actually this is the FIFO. So the instruction order is not mixed in the instruction fetch queue actually, but the speed, the frequency of processing in decoder state, decoding stage is very diverse. So we need the instruction fetch queue here, and then the decode send the instructions out of order. So, and the instruction is decoded, and instructions are sent to the target execution unit, and then actually we don't know when the decoded instructions are executed by target execution unit, because each out of order execution. So which means that we need also queue before execution units of the system. Queue, queue, and queue. So decoded instructions are sent to the target queues of the execution unit. Then execution unit execute the instructions in these queues when the instructions are ready for execution. Okay, so these queues are called issue queue. Okay, then when the date also the cache has the variable execution time based on the hit or miss of the request. So which means that we need also need queue before address generation unit and then data cache. So if we just compare the statically scheduled architecture and then some enhanced architecture for out-of-order processing, then we just add some queues. Okay, some queues between the execution unit. Sorry, from instruction batch to the decoder. Also, we need some queues between the coding stage and then execution stages. Also, the memory has the variant service time. So, to an extent, we need also queues. So it's a very basic digital design policy. So we can rewrite the structure of out-of-order processor like this. Okay, actually it's the same figure. So I draw this architecture so horizontally, but this Thomas algorithm architecture is represented vertically. Okay, and it's the same. So this is the instruction fetch stage. And then, as you can see, this is the instruction fetch queue. And then, when the instruction which is the end of the instruction fetch queue, and then instructions are decoded and then dispatched. So this event is called dispatch, which means that instructions are decoded instructions are sent to issue queues. So issue queues of the target execution unit. So these queues are called issue queues. Okay. And then, as I said, we can find also another queues between address generating unit and then data cache. Okay, so we need to also consider the orders of load and store in data cache. That's why we need to have the two queues, load queues and then store queues. So which means that we need to also consider the orders of load and store instructions that access data cache. And then, as you can see, this is a CDB, it's a common data bus. So the result from each execution unit need to be written back to the target register files, right? In integer registers or floating point registers. So here, the common data bus, the data is delivered to the target registers. So this is the architecture of out-of-order execution. And then actually, this algorithm, this architecture is called the Thomas-Low algorithm. So, and then if we took the current architecture, actually in the last semester, and I explained about the Thomas-Low algorithm very intensively because it's a very important issue. Actually, it's a very important for the architecture of the modern CPU. But I briefly explain. Okay. So this is the Thomas-Low algorithm, and then so actually in the Thomas-Low algorithm, the instructions are fetched in order, and then and also instructions are dispatched in order. Okay, that's in order until that is front end, and then And the instructions are issued to the each issue queue here. So instructions can be issued to this integer issue queue, and then memory issue queue or floating point issue queue. So, as for example, let us assume that this is the add R1, R2, R3. So these are operands, source registers. So once the instructions are issued to this issue queue, then processor check the readiness. The readiness of the operands of the instruction. And then if the instructions are ready, then any instructions. So make it this is the add. Let us assume that I need to avoid touch screen. So this is the add, this is the move, this is the sub. And then even though the instructions are dispatched in order, the processor check the readiness of instructions by checking operands of our instruction. And then if the instructions are ready, then these ready instructions are issued to the execution unit, then it's executed, then the result is delivered via common data bus. That's how the out-of-order execution unit, out-of-order processor works. Okay, actually it's very simple, right? Only change is that instructions are included in the issue queues, and then in the issue queues, we just check the readiness of instruction, and then if the certain instruction is ready, then the instruction is executed, and then the instruction is written back to the register file. So also it is true that we need to check the low hazard, wow hazard, and then war hazard. Okay. Actually, it's very simple. It's very simple to check the low hazard. Also, in the Thomas algorithm, wow hazard and war hazard are also checked in the issue queues, and then I will skip the detailed architecture. So which means actually I said we need to check the wow hazard and war hazard, and then this wow hazard and war hazard are checked in the issue queues by checking the issue queue entry. Okay, it's very similar to the register renaming. Okay, then this is written back to the register file. That's the problem. So actually, with the Thomas algorithm, we handle this issue, the all data hazard in register file. Also, with the load queue and then store queue, we can also handle the data hazard in memory. So data dependencies in main memory. But this and this is not handled by Thomas law algorithm. So the problem of Thomas law algorithm is that, so as I mentioned, in the Thomas law algorithm, so this out-of-order process architecture, the instruction is executed here. The ready instructions are executed out of order. And if the instruction is executed, and then the result is written back to the register file. And then once the data is written back to the register file, then it's very hard. Actually, we cannot revoke this result. The problem is that branch instruction. So as I said, when the branch is executed, then we have diverged path, diverged execution path by the result of the branch. So in the Thomas algorithm, when the instructions in this path is executed through path, Then every result, these results are also updated to the register file, also main memory. But if this expectation is incorrect, then need to erase this result. But this is not supported by out-of-order or the execution and out-of-order execution processor. I explained Thomas algorithm. So the main drawback of Thomas algorithm is that when the branch instruction is the branch instruction is encountered, then the execution is to be stopped at the branch instruction. Okay, that's the main disadvantage of Thomas algorithm. So the problem is that actually, in order to support the out-of-order execution, then we invest more hardware resources such as the many queues. Then actually the control is very complex, okay, compared to the statically scheduled pipeline architecture. But we have only 4 and 5 instructions which can be executed concurrently. Also, the precise exception is not supported. So think like this: when once the instruction is executed, then the state change. So state changed by this instruction is permanently updated to processor. And then the exception is defective. So which means that we cannot roll back this exception, the execution of this instruction. So actually the precise exception not supported by Thomas algorithm. So we need to support the speculative execution. So the main idea of speculative execution is that it's not actually. So how can we solve this issue? The issues by Thomas algorithm. So which means that the issue. Actually, the problem is that in the Thomas algorithm, once the instruction is executed, okay, then the executed results are updated immediately. Okay, so which means that updated means that it's written back. The results are written back immediately once the instructions are executed. That's the problem of the Thomas algorithm. Then how can you solve this? So simply, if the result of instructions are not updated immediately, here, then we can solve these issues, like branch instruction issues in branch instruction, also the issues in precise exceptions. Then how can we delay the update, the write back of executions? Memory. So which means that if we just have temporal memory component, so if we have temporal memory component, and then the result of executions are just stored in this temporal memory component temporarily, then we can delay the write back of the executions, which means that we can delay the updates of executions. Okay. So also with the We can also support the predicted execution, it's called the speculative execution with this temporal memory component, right? So think like this. This is the branch, and then this is the true path, and this is the false path. And so these instructions, true path instructions in true path are executed. The result of these instructions are temporarily stored in this memory component. Okay, and then we detected that the result of a branch are incorrectly predicted. Oh, this was wrong. And then we can just erase this result, and then we can execute the instructions in both paths, right? So if we have memory component which can store the result of out of execution temporarily, then we can solve these issues. So the issues in branch instruction also the precise exceptions. Okay, you understand? So actually these are also this design approach can be commonly also applied to many process architecture, which means that which means we can delay the update of some request or result if we have some temporal space for storing temporal result. And then if the execution of these instructions are confirmed, okay, then we can can perform the write back of this result. This is the main idea of the speculative execution, and then in order to support the speculative execution, we have this memory component called ROB, the real buffer. Okay, so ROB is the real buffer. So as I explained, ROB stores the temporal, the result of instruction execution temporarily. Okay. And then when I explain about the Thomas algorithm, so the Thomas algorithm so we have instruction fetch, instruction decoding or dispatch, execution, and then write back. So instruction fetch is the in order in the Thomas algorithm. Instruction decoding is also in order. So and then execution is out of order. Okay. So instructions can be executed out of order. That's the main feature of Thomas algorithm. About the write back. Write back is out of order. Okay. But in order to support the issues in order to handle the issues in branch instruction, also in order to handle the issues in exceptions, we want the write back is in order. So which means that it's the order of instructions. Okay. Only part is execution part, execution stage. If the instructions can be executed out of order, then we can exploit the instruction level parallelism. Okay, we can increase the instruction level parallelism. So that is the Thomas algorithm. But you want the write back is also in order in order to support the branch instruction and then precise exception. So speculative execution with the Thomas law and ROB, so reloadable from here. So, but as you can see, the dispatch decoding is also in order. Okay, only the execution is out of order, so which means that so this is the ROB, and then when an instruction is dispatched, so which means that the instruction is decoded at the end of the instruction fetch queue, and then the decoded instruction is given to us. It's sent to the parallel issue queues of the execution unit. So when the instruction is dispatched, then this instruction is registered in ROB, because we need to log the instruction order. So it's the dispatch order, okay? Because the dispatch is in order. So which means the instruction is dispatched, the dispatched instruction is recorded in ROB, so registered. And when the execution, when the instruction is executed, the result is not written back immediately. As you can see, the result is written back to the ROB. Okay, so it's something like this. Oh, this is the add instruction. I wanna execute the add instruction here at R1, R2, R3. So this is the destination of the add instruction. So when this add instruction is dispatched, so and then this add instruction is registered in ROB, so ROB. And then when this add instruction can be executed if these operands are ready, then the executed and result of add instruction R1 is also stored in ROB. It's not written back to the register file. Okay. Then let us so add R1. So something like add R1, I2, I3, and then sub I4, I5, and R1. So we can also find the data dependency between add instruction and sub instruction because of this is a raw hazard. Okay, so in this case, this sub instruction can be also executed because this result are temporarily stored in the ROB. Okay, because when after this add instruction is executed, the result of add instruction is stored in the ROB, and then when the sub instruction is executed, and sub instruction can use the result stored in the ROB. Okay, and then the sub instruction is executed, the R4 is also stored in the ROB. Then when the instructions are written back, so actually this stage is called the commit, because the result of instruction is updated to the processor, and then this is called commit or retire or graduate. Okay, so sometimes we have so, and the instruction is the result of the instruction is updated to processor, and this is called the commit or retire or graduate. Okay, so this table has a different name. Okay, but so I use commit. So when an instruction is committed, then the result, the temporarily stored result are written back to the register file. Here, as you can see, ROB is connected to the registers, register files. So it's written back to the register file. That's how the speculative execution is supported by Thomas law with ROB. Okay, it's simple. It's not simple, but if you understand the basic policy and then why these components are required, I believe you can understand how the speculative execution or use the buffer is implemented and then used in the processor architecture. So actually, so as I mentioned, so in the add instruction is dispatched and this add instruction is registered in ROB, and then which means that the destination, the result of add instruction is the R1. So R1 will be updated. Then R1 will be registered in, also stored, will be stored in ROB. What does that mean? So actually we change this R1 into this location, right? So when the after add instruction is dispatched, and then if the following instructions it require result from this add instruction, then following instructions need to find this data R1 from ROB, right? So which means this R1, it is equivalent. It is, we can say that this R1 is changed to the ROB entry number. Okay. So which means that the following sub instruction, instead of R1, we need to access the ROB entry number of add instruction instead of R1. So this is controlled by register alias table. Okay. So as I mentioned, when the add instruction is dispatched, then add instruction is registered in ROB entry, and then after that, the following instructions need to access the ROB now to get the result of this add instruction. So which means that if you want to read data from R1, then you need to access this ROB. So which means the processor need to change the destination register of this following instruction. So this is done by register alias table, so called the RAP. So in the Thomas algorithm, we add the buffer and then register alias table to support the in order commit. The execution is out of order, but commit is in order. Then in order to handle the performance drops by branch instructions, we add the branch prediction buffer called the BPB and then branch target buffer BTB. So, and then I already explained how the branches are handled in this Thomas law with speculative execution. Okay. So, okay. So actually, compared to the actually this is a little bit tricky part in the process architecture, but if we just understand how the instructions are executed, and then what are the performance issues in the statically scaled pipeline architecture, and then in order to solve these issues, then we apply the out-of-order execution. Okay, and then in order to support the out-of-order execution, then so we also encounter the additional issues, the branch instruction and precise exception. So, which means we want in order commit, even though the executions are executed out of order. So in order to support the in order commit, Then we add the ROV register is table. And then in order to handle the issues in branch instructions, we add branch predictor and then branch target buffer. Okay. So I hope you can understand how the processors are advanced. Processor architectures are advanced for increasing instruction level parallelism. It's okay. The target is obvious. We want to increase the number of instructions which can be executed concurrently. That's the target of this process architecture. Okay, but what's the problem? Oh, it's hard to understand. Which means that the controls are very complex. Controls are complex. Hardware is also complex. It requires more hardware resources. As you can see, we add many queues here. Also, we add ROV, so it's the additional storage for temporal data. Also, branch predictor and branch target buffer is also the memory components. Okay, right? I will explain about the branch predictor, but branch predictor and branch target buffer is called buffer, which means that it's also memory component. So, which means a processor includes many memory components, and they also speculative execution supports the this instruction is executed with a branch instruction. But our prediction was wrong, so incorrect. Then we need to cancel these instructions. So which means that these instructions are executed, so it means that the power is consumed. But even though more power is consumed, but this power, the power consumption is wasted. It's not used for correct path of the branch instruction. So we need to cancel these instructions. So which means more power is required. More power is consumed. So that's another issue of the complex hardware design. Even though the performance can be improved, the process architecture becomes very complex, which means the hardware, we need to invest in more hardware resources, and also the power consumption is also issues. Okay, which means that it's very complex. Okay, so this is the example of how the instructions are executed in the speculative Thomas law, with the speculative execution. So until now, so I explained some dynamically scheduled the pipeline architecture. And then, as you can see, the target is obvious. So we want to increase the number of instructions which can be executed simultaneously. So which means we want to increase the instruction level parallelism. Then in order to increase the instruction level parallelism, we require complex architecture or hardware. So we can increase the performance, but power is also increased. That's the problem. Then so we need to change the target. So which means that with the instruction, so not to increase the instruction level parallelism, we require very complex hardware architecture. Then how can we? But we can also increase the performance with the thread level parallelism. Okay, so which means that also we can also increase the performance by using parallel processing. So it's very similar to the increasing throughput. So actually, when we focus on the instruction level parallelism, we focus on the latency. latency of a program, latency of a thread. But we can also focus on another performance metric called throughput. So, which means we can increase the throughput with the parallel processing. So it's the processor also, process architecture has been also advanced for increasing the thread level parallelism or throughput of workload. Okay. So let's break 10 minutes. Then I will also explain about the parallel processing architecture, like also. Okay. The CPU was a traditional process architecture. Okay, let's take a 10 minute break.
인용도를 인용을 받았는데 그거를 수행자가 보내줄 때 필요 안 해서 봤어요. 익셉션에 레드미를 해가지고
레디
식으로 하게 됐어요.
그렇죠. 걔는 이제 그 파이퍼가 아니라 걔는 이제 그 거기서 그 오더가 이제 섞일 수가 있는 거죠. 그러니까는 이렇게 생각하면 파이프 우리가 보통 뭐 우리가 보통 파이프라고 하면은 그냥 여기 이제 센더가 있고 여기 리시버가 있을 때 센더랑 리시버의 프로세싱 스피드가 다른데 그냥 오더만 이제 똑같이 이제 우리가 해주겠다 하면 그냥 파이프 붙이지 않나요? 요거는 그냥 이 오더를 이제 맞춰서 가는 건데 지금 뭐 인스트럭션 백스큐나 이런 것들은 이런 파이프 구조를 가지고 있는데 뭐 여기 인스트럭션 1, 2, 3 이렇게 간단하게 하더라도 얘가 먼저 수행될 수 있는 구조를 설계하는 거예요. 얘는 파이프가 아니에요. 그냥 저장해놓은 그 메모리에 저장해놓은 다음에 이 엔트리가 이제 레디가 됐네. 이 엔트리를 먼저 실행시킬 수 있는 구조로 되는 거예요. 네.
프레사이드 익셉션이 한국인과 떨어져 이제 그래서 이제 수업을 듣는데 이 프레사이드 익셉션하고 프레사이드 익셉션인데 이 프레사이드 같은 경우에는 프로그램을 종료시킬 때 이태편이 발생했기 때문에 저희가 신경 쓰지 않았겠지만 저희가 주어들어요. 프레사이드 익셉션 같은 경우에는 오버플로우라든지 그런 문제가 발생해요.
그렇게 이제 프리사이즈 익셉션이냐 인프리사이즈 익셉션을 그런 식으로 이제 구조라는 건 아니고요. 얘는 익셉션을 어떻게 우리가 처리를 할 거냐 그거를 가지고 구조를 하는 거예요. 아까 말했듯이 익셉션은 우리가 인스트럭션 오더대로 완벽하게 처리를 해줄 거냐 요거를 이제 우리가 프리사이즈 익셉션이라고 하고요. 근데 아까 말했듯이 토마스로는 프리사이즈 익셉션을 제공할 수는 없어요. 걔는 EXP가 끝나면 무조건 다 적어버리기 때문에 그 토마스로는 기본적으로 imprecise exception이에요. 그 imprecise exception은 뭐냐? 하드웨어는 exception을 고려를 하지 않고 exception을 instruction order대로 고려하지 않고 그냥 exception이 발생했어.라고 그냥 보내주는 거예요. 그럼 소프트웨어가 그거를 좀 분석을 해서 얘를 이제 좀 내가 처리를 해주겠다라고 하는 게 imprecise exception. 그러니까 인스트럭션 오더대로 익셉션을 처리하는 게 아니라 그러니까 섞일 수 있다는 거죠. 그래서 그냥 뭐 지원은 그렇게 익셉션이 발생하면은 어쨌든 이게 왜 발생했는지 그걸 소프트웨어는 알아야 되잖아요. 그냥 그 소프트웨어가 그거 알아서 처리를 해주는 거죠. 크리티컬하다 이건 하나요.
프레사이드 익셉션은 인오더 순서대로 처리를 해야 되는데
그렇죠.
컨솔로는 이제 그게 안 됐어. 저는 바로 보면
아웃 오브 익스큐션 되고 그 익스큐션 된 게 바로 이제 프로세서 업데이트가 되기 때문에 서포트할 수 없어요.
보완하기 위해서 ROD라는 코드를
그렇죠.
만든 거서 프리사이즈 익셉션에 참여할 수 있다고 선택했다.
네, 그 익셉션은 이제 프리사이즈 익셉션을 서포트를 할 수가 있는 거죠. 왜냐면은 익셉션을 이제 리포트를 하게 될 때 커밋할 때 이제 리포트를 하면 돼요. 그러니까는 익셉션, 그러니까 하드웨어가 익셉션이 이제 발생한 그런 리즌을 저장하고 있는 거예요. 저장하고 있지만 얘를 리포트를 하진 않아요. 얘를 리포트를 할 때는 아니라 인스트럭션이 커밋이 돼요. 근데 이게 왜 중요하냐면 이렇게 생각을 하면 되죠. 여기 브랜치가 있는데 이게 true고 이게 false여서 여기서 했는데 여기서 익셉션이 발생했어요. 근데 사실 얘는 그 스페큘레이티브하게 익셉션인 거잖아요. 사실은 코드가 열로 안 갈 수도 있다는 거예요. 근데 익셉션 발생하니까 내가 바로 이렇게 보내주면은 어차피 여기는 코드 안 가는 건데 얘는 익셉션을 처리를 해줘야 되잖아요. 그러니까는 실제로 이제 우리가 이제 실제로 어디 갔는지 알 수 있는 거는 커밋이 될 때거든요. 그러니까는 여기서 커밋이 될 때 익셉션이 여기서 발생했네 하고 리포트를 시켜주는 거예요. 그러면은 이제 익셉션을 이제 처리를 해주면 그 소프트웨어를 이제 받아서 그 익셉션 핸들러 돌려서 이제 처리를 해주고 그렇게 할 수 있는 거죠. 커밋이 되면 커밋. 계속 기다리고 있는 거죠. 익셉션 어차피 말했듯이 레어한 이벤트이기 때문에 가지고 있다가 OS 발생한다. 그래서 리포트만 해주면 OS가 알아서 처리를 해주는 겁니다. 네, 그 프로세서 아키텍처에 대해서 좀 설명을 하는 이유는 어쨌든 우리가 이제 아키텍처가 이제 그렇게 이제 쉬운 분야는 아닌데 하드웨어를 아무래도 다르기 때문에 근데 이제 결국에는 이제 컴퓨터를 연구하는 사람으로서 그 아키텍처가 왜 이렇게 이제 보완이 되었느냐 이를 이제 이해를 해야 되거든요. 이게 왜냐하면은 결국에는 뭐 모든 소프트웨어나 뭐 하드웨어나 모든 엔지니어링이 마찬가지긴 하지만 결국에는 문제, 그러니까 이슈가 무엇이었느냐, 그러니까 어떤 이슈가 있었느냐, 그러니까 문제가 뭐 있으면은 그거를 이제 해결하는 게 엔지니어링이기 때문에 결국에는 아키텍처, 그러니까 프로세스 아키텍처도 뭐 이런 이슈들을 어떻게 하면 해결할 것이냐 이런 식으로 이제 발전을 해왔어요. 그러니까는 CPU 아키텍처가 뭐 지금은 굉장히 이제 복잡하고 뭐 CPU 설계하는 회사가 뭐 옛날 같으면 인텔하고 AMD 요새는 좀 많이 늘어나긴 했는데 그래도 ARM 프로세서를 설계를 하면서 어쨌든 결국 이런 구조로 이제 가게 된 이유가 그 인스트럭션들을 어떤 식으로 이제 처리를 할 거냐, 어떤 문제가 있었느냐. 뭐 결국에는 우리는 그 엔지니어들은 두 가지 말이잖아요. 퍼포먼스랑 코스트. 퍼포먼스를 어떻게 하면 늘릴 수 있느냐. 그다음에 코스트가 어떻게 하면 줄일 수 있느냐. 코스트는 뭐 여러 가지 파워랑 그다음에 뭐 하드웨어 리소스랑 뭐 에너지랑 그걸 해야겠죠. 그 두 가지를 이제 두 가지 이슈를 어떻게 해결했느냐 여기에 이제 초점을 둬서 이제 아키텍처가 이제 발전을 해왔고 GPU도 사실은 뭐 처음에 뭐 첫 시간에 설명을 해주긴 했지만 그러니까 그래픽스 어플리케이션 어떻게 하면 우리가 빨리 돌릴 수 있을 것이냐 CPU로 돌리는 데는 아무래도 한계가 있기 때문에 뭐 경험해봤잖아요. 뭐 좋은 GPU 쓰면 게임도 막 잘 돌아가고 게임도 막 그 FPS 프레임 퍼 세컨드도 늘어나고 그다음에 좀더 깨끗해지고 뭐 그런 거 많이 경험을 했잖아요. CPU가 그것을 다 처리하기에는 좋은 구조를 가지고 있지 않기 때문에 그렇게 발전을 해온 건데요. 근데 어떻게 하면은 근데 이제 우리가 이제 여기서 이제 배우는 거는 GPU잖아요. 제너럴 퍼포즈. 여기는 어플리케이션을 어떻게 실행할 거냐. 그래픽스뿐만 아니라 어떤 어플리케이션, 제너럴 퍼포즈 어플리케이션이 들어왔을 때 얘를 어떻게 하면은 또 효율적으로 이제 실행할 수 있느냐. 그런 거를 이제 고려를 하면서 GPU도 이제 발전을 해온 거고, 그냥 뭐 그래픽스만 이제 처리한다고 하면은 그냥 첫째 날에 설명한 것처럼 그냥 그래픽스 파이프라인 그것만 제대로 하면 돼요. 그렇지만 이제 지금은 그게 아니잖아요, GPU가. 그래픽스 파이프라인만 일단 A식처럼 이렇게 동작하는 게 아니라 그냥 모든 어플리케이션을 지금 돌리고 싶어하는 그 엔비디아의 그 타겟 골인데요. 모든 어플리케이션을 GPU로 돌리게 하겠다. 쉽진 않죠. 어쨌든 그것을 위해서 이제 발전을 해온 거고, 그러려면은 우리가 이제 CPU 구조나 이제 어떤 프로세서 구조에서 이런 구조가 왜 나왔는가? 결국에는 우리 뭐 이 분야도 마찬가지지만 뭐 새 거가 없어요. 과거로부터 배워야 돼요. 네. 어떤 옛날에 있었다 말 그대로 뭐 애플이 뭐 제품 잘 만드는 게 아니라 사실은 옛날에 나왔던 아이디어 다 이렇게 써가지고 그걸로 구현을 해낸 거잖아요. 아니 뭐 리서치도 지금 워낙 좀 리서치 뭐 여러 가지 아이디어들이 많이 이제 발전을 해왔고 진짜 완전 획기적인 아이디어가 이제 등장을 하는 거는 진짜 초창기 어떤 기술의 초창기에는 어떤 획기적인 아이디어로 그것이 막 크게 변하고 이런 것이 가능할 수 있었을 텐데 이게 어느 정도 이제 기술이 이제 세츄레이션 되고 이런 시기에는 결국 우리는 예전에는 어떤 게 이제 발전을 했는지 그다음에 어떤 이슈가 있었을 때는 어떻게 풀었는지 이런 것들을 보고서 또 새로운 아이디어를 또 내고 이럴 수밖에 없어요. GPU도 좀 보면은 뭐 이게 뭔가 새롭다. 사람들은 새로운 구조다 이렇게 얘기를 하지만 결국에는 거기에 들어가 있는 아이디어들은 우리가 CPU에서 배웠던 그런 아이디어들이 하나하나 다 녹아 있습니다. 그러니까 그런 것들을 이제 생각을 하면서 GPU 구조를 이해를 하면은 이제 도움이 되고 그렇기 때문에 지금 이틀 정도, 2주 정도를 지금 좀 리뷰하는 식으로 설명을 하고 있고요. 그리고 물론 이제 이거를 저번 학기 때 이제 그 어드밴스드 컴퓨터 아키텍처를 만드는 학생도 있기 때문에 어려울 수도 있긴 한데 그래도 기본 그러니까는 왜 이게 어떤 그런 이유로 왜 이런 아키텍처가 들어가 있나 그런 거를 생각을 하면서 좀 들으면 좋을 것 같습니다. 나중에 GPU 할 때도 여러 구조가 나오겠는데 여기가 들어간 이유가 왜 그게 됐는지를 배워놓으면 어느 정도 도움은 될 거예요. Okay. Okay. Let's resume the class. So until this slide, I explained about the advanced computer architecture, advanced CPU architecture actually. So as I mentioned, these architectures are applied for increasing the instruction level parallelism. But as I explained, the hardware becomes very complex and also it's very tricky to understand. So actually, we can also have another direction for improving the performance, another performance metric, throughput. So let's talk about the instruction and data. It's very, I believe everyone knows about this taxonomy, the Blaine's taxonomy, and it's very popular. So actually, the Blaine's taxonomy classifies the process architecture based on instruction and data streams. Actually, very simple. So we can use the single instruction and the multiple instruction. So there's the instruction streams, and then we can use the single instruction or multiple instructions. Also, with the single instruction, we can handle the single data. So actually, it's a scalar data. Or this single instruction can handle multiple data elements, such as the vector data. Okay, so it's a single, actually it's a scalar. The multiple each vector. So based on the single instruction and multiple instructions and so single data and the multiple data, we can classify the process architectures. SI is single instruction, single data is the SISD, and then single instruction and multiple data is the SIMD. Then multiple instruction and single data, it's very inefficient. So, for example, and then multiple instruction, multiple data. It's actually this multi-core. Okay, so and then multi-core architecture, and then each core handles the single instruction and single data. The CPU architecture. So it's the intention of multi-core architecture. And then single instruction, single data is the actually very typical processors. Okay, like the add R1, I2, and I3. So if you see this instruction, then we can find that single instruction add. Because single instruction is instruction handles scalar data. R1, I2, actually each element, each register has single data element. That's why this is called the SISD. But we can imagine different instructions like add B, so it's a vector, so B1, B2, and B3. And then only difference is that this add instruction and this the vector type data. And then what is the vector? In the vector, there are multiple elements. So add that means that is the vector, it performs vector addition. So this type of instruction, this type of processor is called SIMD processor. It's a single instruction and multiple data. And then as you can see, actually the most of the processor supports the SIMD instruction. Okay, because many popular applications such as the multimedia applications like video, music, some image applications. Actually, these type of applications handle vector type data. And then if the vector instructions are supported by a processor, then we can accelerate the performance of this type of multimedia applications. That's why most of the processor supports the SIMD type SIMD type processor, SIMD instructions. So as you can see, x86 the Intel processor also support the SIMD instructions such as SSE. Okay, so that's why we can hear the MP3 or we can play the videos using Intel CPU. Okay, the SIMD. If we just focus on the SIMD, this type of instruction is very different from the scalar instructions like add, R1, I2, I3. So actually until now, we want to increase the instruction level parallelism. So which means that we want to increase the number of instructions. But SIMD is different. Actually, it's a one instruction, single instruction, add that 3. So actually, the number of instructions is the same, but size of data, B1, B2, B3. So this is the vector type data. So multiple instructions can be executed by a single instruction. So instead of increasing the number of instructions, we can increase the number of data elements. So target is different. So actually, the target of the advanced architecture is to increase the instruction level parallelism, but it's a single type instruction. It's just increase the size of data handled by a single instruction. So it's called the SIMD. So why am I emphasizing this SIMD? Because it's GPU architecture. Actually, the GPU architecture is very similar to SIMD. So, did I mention? I don't know. But actually, the GPU architecture is called the SIMD. But it's just look, the GPU architecture just looks like SIMD. Actually, the inside of the GPU architecture is designed like SIMD architecture, like single instruction, multiple data. Why? Traditionally, in order to handle the size of data, SIMD architecture is efficient compared to other it's scalar architecture. So it's a SIMD. And then, as I mentioned, SIMD architecture just handles the vector type data. And what is the disadvantage of SIMD architecture? So with the SIMD architecture, like X.V, B1, B2, B3. So actually, for arithmetic or logical instructions, you can easily apply SIMD instructions because these instructions can handle vector type data. But control instructions, like branch, and how can you handle the branch instructions with the SIMD architecture? So if you see the branch instructions such as the if A equal B, then blah blah blah. So what is the typical execution model of the branch instruction? We just check the value of scalar data like A and B, and then we just compare we just check the scalar data values, and then the branch can be true or false, the result of the branch. And then based on this branch instruction, then we can execute the different instruction path. So actually, because typical branch instructions handle scalar data, it's not easy. With the SIMD architecture, it's not easy to support branch instruction. So it's true that we can support the branch instruction with the scalar instructions. Like we can also support the branch instruction like in the typical with type instructions. And then after the branch instructions, then we can also execute the SIMD type instructions. So typically, most of Intel or ARM processors looks like this. Actually, this is the normal CPU, the normal CPU, and then actually the SIMD engine is attached to the CPU. So which means a SIMD instruction is given to the CPU, and then the SIMD instruction is just given to SIMD engine. Then other scalar instructions are executed by normal CPU architecture. Then SIMD instructions executed, which also return back to the vector type register. Okay, RFP. That's how the SIMD instructions are executed and processed in a typical CPU. Okay, either because we need this branch instruction, and here it's very difficult because the branch instructions just handle the scalar data. So also the another disadvantage is the memory instruction, like load. So actually, in the next class we will also cover the architecture, vector process architecture, or the array processor architecture. But so typically, we can easily handle the vector type instructions using many processing engines. So for example, we used here. So add V, V1, V2, and V3. And then we already know that is the vector type data. And then in order to accelerate this vector type data, you can just, this is the P1, is P2, the P3, and then we can just implement the parallel execution engines for handling vector type data. And then this can be also stored to vector type register file in parallel. So which means it's just the vector type register file. So the register actually is very large because the many elements can be stored. So we can use the very large memory component to handle the register file, the type register file. But problem is the memory instruction like load and store. So we already know that if the sequential, so actually, just a moment. So this is the data cache, and then data cache has the fixed width, and then actually, if the actual data cache has the limited number of ports, okay, read port and write port, and then actually, even though the vector type data has many elements, in order to access the, in order to load these elements, we need to access the data cache serially, okay, not in parallel, okay. So even though we can accelerate the execution using the parallel processing engines, the memory access should be serialized. That's another issue. But we already know that if the data is well organized, so which means that it's a sequential access, and then so it's like the elements are organized in the memory space, then the performance it's efficient. So we can access the data very efficiently in the main memory, like DRAM. But like this, A and B, I. So this is the indirect access. The element number of array A is determined by the data of array B. That's by I. So if I is the, so we already, if the I is the like 0, 1, 2, 3. So it's a sequential, but this result of B is it's random, right? So which means that we can just access the multiple element like this form, but because this is the indirect access, so if every element of the vector type data need to access the irregularly assigned data, which is also it should be realized in the memory hierarchy. Also, it's very inefficient. So large number of requests should be generated from the vector type load instruction. It should be handled by memory hierarchy. So it's a heavy burden to the memory hierarchy. So even though the processing can be accelerated by parallel processing, but the memory instruction cannot be easily parallelized. As I said, the control hardware is the problem. So actually, this SIMD architecture is applied to in specific type of instruction, like multimedia instructions, because this type of instructions handle the vector type data. Then actually this SIMD architecture can be applied to specific type of instruction. Okay. And then let's think about the multi-threading. Now, what is multi-threading? So actually, when I explain about the SIMD architecture, it just increase the size of data. And what is multi-threading? So as you can see, this is the multi-threading, which is can support the multi-thread. Okay, so it's similar to TLP, thread level parallelism. Okay, multi-threading means that with one core can support multiple threads, multiple concurrent thread. What is the concurrent thread? The thread, the independent instruction streams. So actually, with a single core, each thread should be executed serially, like thread A, thread B, thread C, thread D, and A is executed, and then B is executed, C is executed, and again, and the A is executed serially. But what's the problem? Oh, we want to increase the instruction level parallelism. So which means that we want to increase the number of available instructions. The problem is that, oh, this is the thread A, and then thread A is executed, and then thread A encounters cache miss. When the cache miss is encountered, then we can execute some other independent instructions, but usually instructions are dependent, right? Because that's how we program code. So if cache miss encounters, then it will take hundreds of cycles, and the data is fetched from the main memory, and process does nothing until the data is fetched from the main memory. Oh, it's waste of cycles. We cannot find any other available instructions in a single thread. Okay, that's the problem. So multi-threading idea is that, oh, if the thread of A is just stuck by cache miss, it's stuck in the processor, and then there is no available instructions, then we can change to the other thread. Okay, thread B. And then thread B can execute some available instruction, and then thread B also can encounter cache miss. Then we can also change to the thread A. Okay, that is the multi-threading idea. Then how can you support the multi-threading? Actually, the idea is simple. In a single thread, we cannot find available instructions if cache miss is encountered. So, then we can change it to other thread. Then the other thread may have the available instructions. Then these instructions can be executed until the thread A is waiting for the data from main memory. Okay, that's a great idea. Then what should we do? In a single core, thread A, the thread B can be changed in a single thread. So while the thread A is being executed, then it is changed to the thread B, then thread B can be executed. So what should we do? What is required? So which hardware components are required? we require register file for thread A and another different register file for thread B. Okay, so actually, so these threads are running on the same computer system. So actually, main memory is the same. Right? So the load instruction is used to access the main memory, also the thread B also share to access the main memory. Because main memory is shared. So what's the problem? So think how the threads are launched in a processor. So which means that how the binary file is launched, it's executed in a processor. Like main function of the C code. So this C code is the binary C code is launched in a processor. The operating system initializes the file, and then operating system writes some pointer of this main function in the register file, and then based on this pointer, then the instruction is fetched from the memory. Also, the instructions are stored in the main memory. So these instructions can be fetched to the instruction cache. Then instructions are executed. That's how the thread is launched and the thread is executed. So thread has the many instructions. Then these instructions will update the register file and the main memory. But in memory is the shared device, shared component. So actually, it will access the register file. But in order to access in order to execute another thread, we need another register file for this thread. Okay. So in order to support the multi-threading, the single core processor has multiple register files which can be assigned to the multiple threads. So for example, Intel has the hyper-threading technology. So with the hyper-threading technology, the Intel one physical core of the Intel core can support the two concurrent threads, which means that we can just actually the Intel has add the more register files in a single core, and actually the number of execution units are the same, the caches are the same, and then so many other hardware components are the same. Only difference is it has multiple register files that can be assigned to the multiple threads. So hardware is the same, but it's a great idea. By investing more register files, and then while the one thread is stopped by some cache miss, then we can execute another thread. Which means, so that's why in the hyper thread, it's called the Intel processor has 4 physical cores, but we support 8 logical cores. Okay, this is the hyper thread. So this is the multi-threading technology that can support the multiple threads in a single core. So the multiple threading, with the multiple threading, we can exploit the thread level parallelism. But it's a thread level parallelism. But now we can also think about some different types of multi-threading, like the fine-grained multi-threading or coarse-grained multi-threading. So it's very a good example, like the coarse-grained multi-threading, fine-grained multi-threading, simultaneous multi-threading. So there are 4 threads: thread A, thread B, and thread C, and thread D. So and then these are instructions. So the modern CPUs supports the superscalar. So which means that multiple instructions can be executed concurrently. So for example, let us assume that the processors can support the 4-way superscalar. Okay. So which means that 4 instructions can be fetched every clock, and then the full instruction can be executed concurrently. And then this is the and this is time, and then these are the instructions of thread A, B, C, D. And as you can see, you can find the empty slots, right? Because of memory instructions. So let us assume that this is the cache miss. So cache miss. Okay. So there are different types of multi-threading. So coarse-grained multi-threading, fine-grained, and simultaneous multi-threading. So coarse-grained multi-threading means that if the cache miss is encountered, then thread is changing. The thread change is called the context switch. Context switch. Okay. So the coarse-grained multi-threading, one thread encounters cache misses, then thread is changing. The context switch is applied. Context is switched. What is fine-grained multi-threading? Fine-grained multi-threading is that the thread is changing every clock. So there are thread A, B, C, D. So here, so at the first clock, the instructions in thread A are fetched and decoded and issued. Then in the next clock, the instructions in thread B are issued. So context switch happens every clock. That is the fine-grained multi-threading. Right, the simultaneous, this is the SMT, it's a simultaneous multi-threading. Actually, this is the hyper-threading of Intel. So simultaneous multi-threading is that instructions can be fetched from any thread if available. It's available, right? So there are 4 slots here. So and then as you can see, at the first line, first instruction, the thread A has the 2 instructions and 3, 3, 1. So actually in the first clock, it fetches the 2 instructions from thread A, and then there are 4 slots here, and 2 instructions from thread B. So this is the simultaneous multi-threading. Okay. So actually, the simultaneous multi-threading is very complex. So Intel was support only 2 threads for physical core, right? But as you can see, hyper-threading can fill the processing slots, and so it's most efficient. But the simultaneous multi-threading requires the very complex control logic or very complex hardware architecture. Why do I explain this? GPU. GPU supports the actually I explained that GPU exploits the thread level terrorism. So which means that GPU can execute thousands of threads concurrently. How? Actually, the same hardware. The GPU hardware is actually very simple. Then GPU hardware, actually there is no branch predictor. There is no interfolding GPU hardware. Then how can GPU hide the latency, execution latency? GPU supports the fine-grained multi-threading. So GPU performs context switch every clock. Okay. So with the fine-grained multi-threading, GPU hide the latency of the execution value. Okay. That's why I explained that this multi-threading. So just remember, so this is very important. So just remember how the coarse grained, fine grained, and simultaneous multi-threading are executed in a single core processor. Then CPU supports this fine grained multi-thread. Okay. Okay. Multi-thread. So actually, as I mentioned, the simultaneous multi-threading is very complex, and it is also complex that it will consume much power. So power. So, and then GPU has many simple cores, and then GPU also implement the simple fine-grained multi-threading because of power issue. Okay, so actually the multi-threading it's a great idea. So from multi-threading we can find more available instructions from multiple thread, but the problem is the complexity. So actually we can implement the high thread level parallelism using the simpler architecture or simpler multi-threading architecture. Okay, so which means that we can add many simple cores and also apply the simple multi-threading for these many simple cores. Okay. Okay. So on this time I will stop here. Do you have any questions? Okay, thank you for your attention. And then the next class I will cover about some basic GPU architecture and then vector and array architecture. Okay. Thank you for your attention. See you in the next class. Yes.
제가 CD가 이제 얘기해 주신 그 애들이 해가지고 이제 벡터 같은 여러 개의 그 데이터 계열들 한 번에 다룰 수 있는 인스턴스를 이제 처리하는 구조?
그렇죠.
네라고 말씀해 주셨는데,
네.
근데 이제 그 구조가 이제 그 구조 설명을 해주셨을 때 여기서 이렇게 이제 변했습니다. 모든 프로세서가 하나의 프로세서에서 처리할 줄 알고.
그 프로세스 인지. 그러니까 이거는 어떤 아까 CPU가
네. 네.
엔진은 이제 할 때는 여기 이제 ALU가 하나씩 있죠. ALU
서로 다른 AL.
그렇죠. AL. 그러니까 요거를 지금 프로젝트를 하는 거예요. 그러니까는
되게 크다고 하나의 코어랑 ALU가
크다는 코어라고 하죠. 걔네들이 코어라고 그러는데 그게 사실은 이게 걔네들은 걔네 코어라고 하는데 코어가 AL.
그럼 그 CMD랑 CMT랑 거의 차이가 없는데
CMD랑 거의 차이는 없는데
CMD가 여러 개냐 아니면 스레드 하나를 쓰느냐 차이라고.
그거는 이제 여기서 이제 더 배우긴 할 텐데 기본적으로 CPU는 CMD 구조를 가지고 있어요. 프로세서 하드웨어는 CMD인데 밖으로 소프트웨어 보이는 소프트웨어를 적으는 이게 CP처럼 그러니까는 프로그래머가 그러니까 유저가 그냥 각각의 트레드가 독립적으로 이제 동작하는 그 시 보이도록 걔네들이 만드는 거예요. 근데 내부적으로 돌아가는 거는 CMD예요.
근데 이 부분이나 그런 건 그럼 어떻게 처리해요?
그런 거 잘 그냥
GLS 네. 혹시 그러면 CMD랑 이제 그 병렬 처리해주는 그 API 중에서 이제 오픈CL이나 이런 푸다나 아니면 오픈MP란 게 있지 않습니까?
오픈MP는 CPU 정도.
CPU 쪽에 있었어요. 그게 막 CMD 저 엔진을 쓰게 해주는 게 아니라.
그건 아니고요. CMD는 인텔이 그거는 이제 인스트럭션을 이제 추가를 하는 건데 CMD 인스트럭션 추가하잖아요. 컴파일러하고 우리 프로그램에 컴파일 하잖아요. 인텔이 항상 컴파일러한테 이제 우리 이런 인스트럭션을 추가했어. 그러니까 이런 어느 부문을 이제 바꿀 컴파일할 때는 이런 인스트럭션을 쓸 수 있어 알려주는 거예요. 그러니까 뭐또 벡터 연산 그냥 우리가 똑같이 이제 코드는 짜는데 그 만약 이제 벡터 연산을 이제 더 잘 할 수 있다면 컴파일러가 그걸 분석을 해가지고 그 인스트럭션을 써가지고 얘를 컴파일을 해주는 거죠. 네, 근데 그 오픈 MP나 그런 거는 그냥 프로그래머가 알아서 내가 여기서 몇 개의 트레드를 생성할 거다 이렇게 해주는 거잖아요. 그럼 이제 각각의 트레드로 이제 독립적으로 이제 생성이 되는 거죠. 그러니까 좀 이게 달라요.
심리랑 다른.
그렇죠. 심리는 이제 그냥 인스트럭션이고
오픈 MP는 그냥 스레디스 멀티코드 여러 개다가 할당시켜서
할당을 시켜서
어레이를
프로그래머가 나는 이게 하나의 코드지만은 여기서 멀티플 트레드를 생성할 거야 라고 이제 해주는 거죠.
다르네.
예.
그러면은 아까 말씀하셨던 GPU 그 심티는 그냥 설계도는 심티로 프로그래머 입장에서 심티로 느껴지지만은 실제 내부 동작은 심티로 동작을 한다라고.
저런 그냥 해야지. 이게 필요할 수밖에 없어.
뭔가 심티로 해야 될 것 같은데 심티로 하면 또 뭔가 약간 그 비슷한데 또 저렇게 나눠야 되나 싶어서.
그 조금 다르긴 해요. 그 말했듯이 GPU 보면은 아까 말했듯이 브랜치 인스트럭션 맘대로 하잖아요. 근데 그러니까 프로그래머는 브랜치 인스트럭션으로 자유롭게 쓰긴 쓰는데 속에 이제 CD처럼 돼 있으니까 사실은 퍼포먼스상은 좋지는 않지만 그래도 서포트를 해주는 거예요. 프로그래머가 마음껏 쓸 수 있게. 네,
프로그래머에게 친화적인 게 CT 구조로 만든 CT 스타일로 이제.
그렇죠. 각각의 트렌드가 독립적으로 돌아가는 것처럼 이제 보여주면은 아무래도 프로그래밍 할 때 어느 정도 자유도가 높아지기도 하고 마음껏 할 수도 있잖아요.
그래서 그래서 GLSL인가 뭐 쿠다 그런 거 할 때 막 if문 같은 거를 최대한 덜 쓰도록.
그렇죠. 큐다
그 브랜치 할 때 그 처리할 때 오버헤드가 발생하기 때문에.
그렇죠.
이해가 됐어.